Hello, in this video we're going to talk about determinants. If you have a square matrix A, any square matrix has a number assigned to it called the determinant of A. And it's written like that. And in this video, we're going to define what that number is, the determinant of a square matrix, and look at some properties. And determinants show up in multivariable calculus. They're related to volumes of certain shapes. When you have a n by n matrix, you can think of that as something that takes vectors in Rn to itself, right? Because if you have a vector x in Rn, you can multiply it by a on the left, and then you get a times x, and that's another vector in Rn. And what happens is you can think of the matrix as transforming the whole space Rn, and the determinant is related to how much A stretches the volumes of shapes. So we'll talk about that later. First, let's just get to the definition of the determinant. Well, there's actually lots of different ways of defining the determinant, but the way I'll define it involves permutations. So I have to say something about permutations. So a little bit about permutations. So let's say that you have the n positive integers 1 to up to n. Now if you write them in a different order, well, not necessarily a different order, but in some order. Say J1 through Jn, this is called a permutation of the integers 1 through n. So you're just writing them in a different order. So for instance, let's say that you have 1 and 2. Well, there's two possible ways to write down these integers. You can write them as 1 and 2, or you can write them in the order 2, 1. So this is one example of a permutation. 1 matches up with 1 and 2 matches up with 2. Or another permutation is to match 1 with 2 and 2 to 1. Or you could have 1, 2, and 3. Well, there's lots of different ways to do it. First of all, any permutation, any 1, 2, 3 up to n, you can just have the permutation that just doesn't change anything. So you can have 1 goes to 1, 2 goes to 2, 3 goes to 3. But of course, there's a bunch of other ones. You can have 1 goes to 1, 2 goes to 3, and 3 goes to 2. And you can also have, so those were the possibilities where 1 goes to 1, but you can also have 1 go to 2. And then 2 and 3 will have to go to 1 and 3. So you can have 2 goes to 1 and 3 goes to 3. Or you can have 2 and then 3 and then 1. And then there's 2 more possibilities. If 1 goes to 3, then 2 and 3 have to go to 1 and 2 in some order. So you can have 2 go to 1 and 3 go to 2. Or you can have 2 go to 2 and 3 go to 1. And this is all the possible permutations of 1, 2, and 3. So there's a total of 6. So this one has 6 permutations. 6 permutations of 1, 2, 3, and there's 2 permutations of 1, 2. And in general, if you have one to n, this has n factorial permutations. And n factorial, just in case you don't know, means you take n and then multiply it by all the integers less than it until you get to 1. Well, actually, if you multiply by 1, you're not multiplying by anything, right? So you can also define it to go up to 2. So for instance, 3 factorial is 3 times 2, which is 6. 4 factorial is 4 times 3 times 2 is 24. Okay, now let's say that you have a permutation. So suppose that you have a permutation. One, 2, up to n. Permutation of 1 up to n. So let's say your permutation is j1 through jn. So your j1 is where your 1 goes, your jn is where your n goes. Okay, then for each ji, count how many integers follow it in this ordering, but precede it in the natural ordering. One to n. Okay, this number is called the number of inversions caused by j sub I. So let's just take a look at an example. Let's say that you had 1, 2, 3, and then you had 2, 3, 1. Right? So this is a permutation. Remember, the permutation is the switching. So this is one permutation. And so J1 is going to be 2, J sub 2 is 3, J sub 3 is 1. So what's the number of inversions caused by J sub 1? Well, when you look at J sub 1, that's this 2, there's 2 numbers that follow it, right? 3 and 1. Now, of those numbers, how many of them come before 2 in the ordering from 1 to n? In other words, how many of them are less than 2? Well, there's 1, right, which is 1. This is the only one that's less than 2 out of the numbers after it. So the number of inversions caused by two is 1. Okay, what about the number of inversions caused by 3? So you look at the 3. How many numbers are after it? 1. And of those numbers, how many are less than 3? 1, right? Because of the 1. So the number of inversions caused by 3 is also 1. And what about the number of inversions caused by 1? Well, there are no numbers that come after it, so it's 0. Okay? So you do that for all those integers. Now let's say you add the number of inversions caused by the j sub I. So in other words, you find the total number. Okay, so you get the total number of inversions which occur in the permutation. That's what the number is called. Now, if the number that you get is odd, then we say that the permutation is an odd permutation. And otherwise, it's called even. So if the total number of inversions is even, then you call the permutation an even permutation. So let's look at the example that we had above. We had 1, 1, and 0, right? When the total number is 2, so the permutation that takes 1, 2, 3 to 2, 3, 1 these are arrows, is an even permutation. Let's look at another example. So let's say that you had the integers from 1 to 6, and you had this ordering 2, 5, 1, 3, 6, 4. So you have this permutation. Okay. Is the permutation even or odd? Well, let's just make a table of the ji and then the number of inversions caused by ji. So we could even just have a column for I. So j sub 1 is 2, j sub 2 is 5, j sub 3 is 1, and then 3, 6, 4. So for j sub 1, which is 2, right, what's the number of inversions that we have that's caused by the 2? Well, there's 5 numbers after it, but of those 5, how many come before it? Well, there's 1, right? So the number of inversions caused by j sub 1 is 1. Okay, what about the 5? What's the answer? The number of inversions caused by j sub 2 is what? Well, for this 5, we see 4 numbers after it, and of those 4 numbers, there's 3 of them that's less than 5. So it's a 3. And then for the 1, it's 0. For the 3, it's also 0, because there's no numbers after the 3 that's less than 3. And then for the 6, it's 1, right? Because the number after it, 4, is less than 6. And then for the last one, it's going to be 0. So if you figure out the total, 1 plus 3 plus 1, right? I add up the numbers, I add up all the inversions, the total number is 1 plus 3 plus 1 is 5. And so therefore this permutation is an odd permutation. Okay? Now when you have an even permutation, we say that the sign of an even permutation, so the sign of an, if I have an even or odd permutation, is 1 or, technically it's a sign, so it's plus or minus. Okay, so the sign of an even permutation is, the sign is defined to be plus, and then the sign of an odd permutation is defined to be minus. Okay, now we're ready to define the determinant. So let's say that you have an n by n matrix. And as usual, we call the ij entry a sub ij. So what do you do to define the determinant? So first of all, you pick out one entry from each row of A so that all the entries all lie in different columns of A. Okay? Now when you have that, you take the product of these entries. So for the first row, you're going to have a sub 1 something, right? So let's call that j sub 1. And then in the second row, you're going to have an a sub 2 something, so let's call that j sub 2, all the way to a sub n, j sub n. So you multiply all these together and you get that. Now you include to this a plus sign or a minus sign depending on whether the permutation J1 through Jn is even or odd. Right? So what's going on is that each row, so for the first row, you pick out a number, it's a sub 1, and then the second subscript is going to be something from 1 to n, so you call that one J1, and then for the second row, you pick out another number, and it's going to be, you know, the first subscript is going to be 2, but the second subscript is something that's different than J1 because you're picking things in different columns also. So you call that subscript J2 and then all the way to J sub n. And what you ended up doing is you ended up having a permutation of 1 through n because you get J1 through Jn. That's just 1 through n in a different order. And because it's a permutation, we talked about the sign of a permutation. And so you include a plus or minus to this product depending on whether your permutation is even or odd. If it's even, you put a plus sign. If it's odd, you put a minus sign. And then what you do is you write down all possible such expressions and add them together. And then the number you get, the number we get, that is defined to be the determinant of A. So that's called the determinant of A. So for instance, let's look at an example of a 2 by 2 matrix, the general 2 by 2 matrix, like this. So one way to pick out a number from each row to keep them in different columns is like this. So you have A sub 1, 1, A sub 2, 2. Now this permutation that swaps 1 to 1, sorry, that takes 1 to 1 and 2 to 2, if you look at whether it's even or odd, this is going to be an even permutation, right? Because if you look at the number 1, there's no number after it that's less than 1, and then for the number 2, there's no number after it at all, and so the total number of inversions is 0, and 0 is an even number, and so this is an even permutation, and so you put a plus sign in front of it. Now for the next permutation, there's only one left, which is to take the A sub 1, 2 in the first row, and then A sub 2, 1 in the second row. So now I have A sub 1, 2, and A sub 2, 1. So I have these numbers, right? I have these numbers, the J sub 1 is 2 and the J sub 2 is 1. When I look at 2, 1, the total number of inversions is 1. Because if you look at the 2, the number after it is less than 2. So 1 and then you know this 1 here is the last number, so there's no inversions caused by that, and so 1 plus 0 is 1, and then you get an odd number, and then you get an odd permutation, and so you put a minus sign. So you have a minus sign, and that's the determinant. That's the determinant of this 2 by 2 matrix. Okay? So if this is A, then the determinant of A is this. It's just A11 times A22 minus A12 times A21. Now let's look at the general 3 by 3 matrix. So you're going to have A sub 1, 1, A sub 1, 2, A sub 1, 3, A sub 2, 1, A2, 2, A2, 3, A3, 1, A3, 2, A3, 3. And we write down all the different possible ways of taking products where you take in each row a number in a different column. So you're going to have A11, A22, A33, and then you're also going to have A11, A23, A32, and then you're going to have A12, A21, A33, A12, A23, A31, and then finally A13, A21, A3, oh wait, that's not finally, and now finally A13, A22, A31. So that's all 6 of them. And you can check that the first one is an even permutation, the second one is an odd permutation, the third one is an odd permutation, the fourth one is even, and then the fifth one is even, and then the last one is odd. So that's the determinant of A. It's this number. Well, now you see the problem with this is that the determinant is going to have the determinant of an n by n matrix will have n factorial terms being added or subtracted, right? So, you know, if you had a 5 by 5 matrix, the general determinant is going to have 120 terms. So this is definitely not a good definition for talking about the computation of the determinant. But it is important for the theoretical purposes. And now I'm going to state some theorems about the determinant. Some properties of the determinant. Okay, one of them is if you take a matrix A and then you swap two rows, you get a new matrix. And then the determinant of that new matrix is -1 times the determinant of the original matrix. That's what I'm about to write down. So if B is obtained from A by exchanging two rows, then the determinant of B is equal to negative the determinant of A. Now remember that when you have this thing, negative determinant of A, that's not necessarily a negative number. That's a common misconception that, you know, a lot of students have, because the determinant of A might itself be negative. So the determinant of A is, you know, -10, then minus -10 is going to be +10. So just because something has a negative sign in front of it doesn't mean it's actually negative, right? Okay, and then another property is that the determinant of the identity matrix is 1. That's something that you can check directly from the definition, because if you have, let's just look at a 3 by 3 matrix for an example, right? If I have this, and I pick numbers from each row and column, so that they're all in different rows and columns, then the only way I can get something that's not 0 is if you took this one, and this one. And then when you multiply them, you get 1 times 1 times 1. And because you're taking A11, A22, A33, 1, 2, 3 is an even permutation. And so you have a plus sign, and then so you don't change the sign, and then you just get 1. Right? If you took a different order, so if you did like this 1, 1, 1, and then 2, 3, and then 3, 2, then you get a 0, right? So the only way you can somehow not get 0 is if you took the permutation that just doesn't change anything. It doesn't change the order. Okay, so that's actually pretty simple to see why that's true. And then the most important one is, well, this can be broken down into like 3A and 3B. So 3A is if B is obtained from A by replacing a row by a scalar multiple of a row. So if B is obtained from A by multiplying each entry in row I by a scalar C, which could be 0, then the determinant of B is equal to C times the determinant of A. So let's just do an example if you take this matrix A11, A12, A21, A22, the determinant of this is A11, A22 minus A12, A21. Now if you take, say, the second row, it doesn't matter which row, but let's say for this example that you took the second one and you multiplied it by C, okay, then if you take this new determinant, well, you're going to get A11, right? You're going to get this number times this number minus this number times that number. Well, what's that going to be? That's A11 times C times A22 minus A12 times C times A21. And now you see that you can factor out the C from this whole thing, from this determinant, and then you're going to get to C times A11, A22 minus A12, A21. And so you see that in this 2 by 2 example, that when you multiply the second row by C, you do in fact change the determinant of the matrix. So here was the determinant of the original matrix. The determinant of the new matrix is C times that. Okay, and this property 3a is saying that that's true for a general n by n matrix, no matter which row you take. And you can kind of think about it in terms of the formula for the determinant. Now what's going to happen is when you take this and then you multiply a single row by C, because you're taking a number in each row and column, you end up getting an extra C term in each of these. You get an extra factor of C in each of these terms, and then you can factor out the C. That's basically the reason why it's true. Okay? So that's property 3a. Oops. That's property 3a, and then 3b is that if B is obtained, it's kind of hard to explain what property 3b is. Property 3b basically says that let's see. I have to introduce some more notation to state property 3b. Property 3b says well, why don't I, because it's kind of hard to state this in general, let me just explain it in the case of like a 3 by 3 matrix. So in the case of a 3 by 3 matrix, so suppose that you have a row. So take a row of the matrix, and let's say that you delete it. Okay. So if you have this 3 by 3 matrix, suppose we delete row 2. Okay. So then you have this. Now let's say that you include something into these rows. So let's say that you have some number x1, x2, and x3. Okay, so you pick some numbers x1, x2, and x3, and then you put them inside that row, so now you have this matrix. And let's say you do the same thing and you pick different numbers. So like y1, y2, and y3. And then you take the determinant of each of these matrices and add them. Then what you get turns out to be the determinant of what you get if you stick in the sum x1 plus y1, x2 plus y2, and x3 plus y3. So this is called linearity in the second row. Well, in this example, it's the second row, but it's in general, it's linearity in each row, I should say, in each row. So let's just say you have an example. Does that make sense? It's what it's saying is if you delete a row and then replace that missing row by x1 plus y1, x2 plus y2, and so on, up to xn plus yn, and then you take the determinant of that matrix, that's what you would get by taking x1 to xn, and then the determinant of this matrix, and then adding what you get if you had y1 through yn, and taking the determinant of that matrix. Now notice that this matrix plus this matrix doesn't equal this matrix. What I'm saying is that the determinant of this matrix plus the determinant of this matrix equals the determinant of this matrix. Well, this is technically, instead of linearity in each row, it's really additivity. I should call it additivity in each row. And when you combine 3a and 3b, it's called linearity in each row. So the determinant is linear in each row. I mean, the way to define it, the way to put this all together is that if you have a matrix A and then you pick a row, so more precisely, if you pick a row A and then let A sub ix be the matrix obtained by replacing row I of A by X. So this is a notation. Then what it's saying is that A sub I x plus y is equal to the determinant of A sub I x plus y is equal to the determinant of A sub I x plus the determinant of A sub I y. That's this condition 3b. And then what 3a is saying is that basically 3a is saying that the determinant of A sub I cx is equal to c times the determinant of A sub I x. That's one way to phrase what 3a is saying. So then what 3b and 3a are combined are saying is that A sub I as cx plus dy, the determinant of that is equal to c times the determinant of A sub ix plus d times the determinant of A sub iy. In other words, so that's what it is saying when you put it all together. And so when you look at, for instance, the 3 by 3 case, it's saying that if you have this matrix, which is A11, A12, A13, and let's say that you work with row 2, although you could work with rows 1 and 3 also. But for us, let's just work with row 2. if you have these two vectors, x and y in R3, and your x is the vector x1, x2, x3, and then your vector y is the vector y1, y2, y3, and you have c and d are constants, then what the theorem is saying is that if you have cx1 plus dy1 here, and cx2 plus dy2 here, and cx3 plus dy3 here, and you take the determinant of this, this is equal to it's equal to c times the determinant of this matrix A11, A12, A13, x1, x2, x3, A31, A32, A33, plus d times the determinant of the matrix A11, A12, A13, y1, y2, y3, A31, A32, A33. So that's what this is saying in the case of a 3 by 3 matrix when you use row 2. Okay? But the theorem, the linearity in each row, says that it doesn't matter which row you take. If you do this, you get the similar result. And this property is probably the most important property of the determinant. This property 3, the linearity in each row. And it turns out that these are characterizing properties of the determinant. 1, 2, and 3 characterize the determinant, meaning that there's only one way to assign to each matrix a number that satisfies 1, 2, and 3, and that's the determinant. And in the next video, we'll use these three properties to calculate determinants more effectively using row operations. You can kind of see how the row operations play a role in 1, 2, and 3, right? Number 1 is if you exchange two rows, that's one elementary row operation. And then number 3 addresses what happens if you scale a row, and then if you replace a row by that row plus a scalar multiple of a different row. Okay, thanks for watching.